All right, Matthew, we got the final lesson in this unit, lesson 7.2.3, applications probability, day 2. All right, so we're just going to do some more probability problems here. It says Shauna has a bad relationship with the truth. She doesn't usually tell it. In fact, whenever Shauna is asked a question, she rolls a die. Dice? Rolls a dice or die? I think it's die. If it comes up 6, she tells the truth. Otherwise, she lies. All right, so she only tells the truth 1 out of 6 times. Okay, so Shauna's going to flip a coin, and you're going to ask her which side landed up. What's the probability that she says heads and is telling the truth? Okay, so there's 2 things happening here. She's going to flip a coin, and then she's going to decide if she's going to lie or not. So in the coin flip, there's only 2 outcomes that we can have. So we can have heads or we can have tails. Now, both of these outcomes are a 50-50 chance, so it's 1 out of 2 for heads and 1 out of 2 for tails. Now, whether or not she tells you it's heads or tails is dependent on whether she's going to lie or not. So if she lies, so she rolls a die, she lies 5 out of the 6 times. So 1 through 5, she's going to lie, and only on a 6, she's going to tell the truth. All right, so let's look at our probabilities on the inside here. So for heads and she lies, that'd be 1/2 times 5/6, which would be 5/12. And for heads and telling the truth, 1/12. For tails and lying, 5/12 again. For tails and telling the truth, it would be 1/12 again. So 1/12 and 1/12, that is 1/6 of the time. 5/12 and 5/12, that's 10/12, which is also 5/6. 5/12 and 1/12, that's 1/2 because it's 6/12. And here we got 1/2 as well. So everything's adding up to 100%, which is what we wanted to do. All right, so what's the probability that she says heads and she's telling the truth? So heads and truth, the probability of heads and truth is 1/12. If Shauna flips a coin and you ask her what it was, what's the probability that she's going to say heads? Well, she's going to say in heads in 2 situations. She's going to say heads. She's going to flip it. It's going to be heads, and it'll be the truth. That's 1/12 of the time. But also, if she flips tails, she could lie and say she has heads instead. So 1/12 plus 5/12, that's 6/12. So half the time, she's going to say that it's heads. Now, she's going to be lying a lot of that time, but half the time, she'll say heads. If Shauna tells you she flipped and it came up heads, what is the probability that it really is heads? All right, so she flipped and it came up heads. So flipped and it came up heads, that's 1/2 of the time. What's the probability that it really is heads? So this is a conditional statement. It did flip and it came up heads. So that's 1/2 or 6/12. What's the probability that it really is heads? So she flips and it's heads. So 1 out of 12. And then we can just multiply the top and the bottom by 12, and we get 1/6 of the time. Is whether Shauna tells the truth or lies independent of the coin flip? Yes. So whether she lies or not doesn't matter whether she flipped heads or tails. She's going to lie 5 out of 6 times. It doesn't matter if she has heads or tails. It's going to be independent. We can prove it's independent because we could always do the probability of A is equal to the probability of A given B. Or we could do the probability of A and B is equal to the probability of A times B. This is probably the easier one to test on this one, because this is exactly what we've been doing. What's the probability of telling heads and a lie? So heads and lying is 5 out of 12. What's the probability of heads? It's 1 out of 2. What's the probability of lying? It's 5 out of 6. And 1/2 times 5/6 is 5/12. So now we can see it's definitely independent. So in this one, our independence test of probability of A times B equals probability of A times probability of B probably makes more sense to test it. But this one we didn't really have to do a test. We could just see that they're not affecting each other. But this is how we mathematically show that they're not affecting each other. Next one, a person's height is independent of their IQ. So how tall you are doesn't change how smart you are. So we're supposed to know that and finish the table knowing that there's a test for independence. So if there's a test for independence, or if this is independent, it should pass the test of independence. So if you have below average height and you have below average IQ, so the probability of below height and below IQ, that should equal to the probability of below height times the probability of below IQ. So I'm using the same test for independence. So right here I see that 50 out of 75, or out of 175. So 50 out of 175, 50. And then over here I've got 70 out of 175. So that should be equal to the probability of A and B, this probability here. And remember, this is going to be over 175. So I want the probability here. I'm calling this part in here X. This is the and. The and should be equal to 50 over 175 times 70 over 175. So if I multiply out the numerator, I would get X over 175 equals 3,500. Now over here I'm going to do something weird. I'm going to do 175 times 175. This is just going to make it easier on me a little bit, because now what I can do is I can multiply both sides of that equation by 175. And then these cancel, and this cancels one of these. So I'm going to get 3,500. X is going to be equal to 3,500 divided by 175. So let's take out our calculator. 3,500 divided, oops, not clear. 3,500 divided by 175, and it comes out to 20. So X would be 20. So now that I know this is 20, that means this has to be 50. That means this has to be 30 because they have to add up going down. And then this one would be 75. And we finished it off. So I'm using my test of independence that the and the probability of the and, if I call this one X, would be X over the total. It should be equal to the probability of below average IQ and below average height. 50 over 175, 70 over 175. So we're multiplying those two. And what I did here is I made it a little bit easier. I multiplied the top, but I just made the bottom 175 times 175, because if I multiply both sides by 175, I can reduce that 175 and just get X, and then to reduce one of these 175s, and I'm left with X equals 3,500 over 175. All right, last problem. We're almost there. A spinner has just two colors, red and blue. The probability the spinner will land on blue is X. If the probability of blue is X, what's the probability of red? So blue is X. What is red going to be called? Well, we know that the two probabilities, if it's going to be blue or red, the two probabilities have to add up to 100%. So the probability of blue plus the probability of red has to equal 100%. So if we know that the probability of blue is X, we know that the probability of red is just if I subtract X from both sides, it would be 1 minus X. All right, so we've got blue, red, blue, red. We're going to do it, so we just said that red was 1 minus X because they have to add up to 100%. So this is 100% minus whatever blue is. Okay, and we said that blue is X and red is 1 minus X. Blue is X, and this is 1 minus X. Okay, so to finish up this table, we would just do X times X, which is X squared. X times 1 minus X would be X minus X squared. X times 1 minus X is X minus X squared. And then over here, 1 minus X times 1 minus X, if you just did a little table here, 1 minus X, 1 minus X, we've got 1, negative X, and positive X squared. So this would end up being X squared minus 2X plus 1. There's our probabilities. So what's the probability of landing on the same color twice? So blue and blue is X squared. Red and red would be X squared minus 2X plus 1. So combine your like terms here, and your probability is 2X squared minus 2X plus 1. The end. All right, good unit. See you back for the next unit. Bye-bye.